Right now, the fastest thing in the universe is light. Nothing outruns it. Nothing matches it. At 186,000 miles per second, a photon crosses the distance from Earth to the Moon in barely over a second. For centuries, we assumed that if we could ever harness that speed, the cosmos would be ours. Every star, every galaxy, every corner of existence within reach. We were wrong. Even if humanity somehow achieved perfect light-speed travel tomorrow, the universe would remain almost entirely untouchable. The distances are too vast. The expansion is too relentless. And time itself conspires against us. This is not a story about why light is slow. This is a story about why the universe is incomprehensibly large. If you enjoy journeys that permanently change how you see reality, hit that like button and subscribe. It really helps out more than you know. Now, settle in and get yourself comfortable. Let's begin. Let us begin with an act of impossible generosity. Forget every engineering obstacle humanity has ever faced. Ignore the energy requirements that would demand converting entire planets into fuel. Dismiss the relativistic mass increase that makes any object with rest mass infinitely heavy as it approaches the cosmic speed limit. Set aside the radiation hazards, the navigation nightmares, the material science challenges that would shred any conceivable vessel long before it reached even a fraction of terminal velocity. Simply hand humanity the ultimate gift: perfect, effortless travel at 186,000 miles per second. 300,000 kilometers per second, the absolute maximum velocity permitted by the laws of physics. Nothing in the universe moves faster, not matter, not energy, not information, not gravity, not causality itself. We are granting ourselves the best that nature allows, the ceiling, the wall, the final word in cosmic speed. At first, this feels like omnipotence. Light crosses the distance between Earth and the Moon in 1.3 seconds. A vessel travelling at this speed could reach the lunar surface before you finish drawing a single breath. The Apollo astronauts needed 3 days to make that same crossing. We have just compressed their journey into a heartbeat. Point the ship toward Mars. At its closest orbital approach, the red planet sits roughly 3 light minutes from Earth. Current spacecraft require 7 months to reach Mars. Our light-speed vessel arrives before a song on the radio finishes its second chorus. The entire transit that dominates years of mission planning, billions of dollars in fuel logistics, and months of astronaut isolation is reduced to the time it takes to brew a cup of coffee. Jupiter, the gas giant whose gravitational influence shaped the architecture of our solar system, lies approximately 43 light-minutes away depending on orbital geometry. Saturn, with its iconic rings spanning 170,000 miles, requires about 79 light-minutes. Uranus takes roughly 2 hours and 40 minutes. Neptune, that cold blue sentinel orbiting at the edge of the planetary family, sits about 4 light hours from Earth. The entire solar system from the Sun's roiling surface out to Neptune's distant orbit measures approximately 8 light hours across. A light-speed traveller could traverse the full domain of our star, visiting every planet, skimming every moon, in a single working day. This is staggering. This feels like the master key to existence itself. Now, aim beyond the Sun's gravitational dominion and point toward the nearest star. Proxima Centauri, a dim red dwarf roughly 1/7 the diameter of our Sun, sits 4.24 light-years away. It is the closest star to our solar system, the nearest possible destination beyond our own cosmic backyard. At 186,000 miles per second, the journey takes 4 years, 3 months, and roughly 2 weeks. Pause on that number. 4 years. This is no longer a day trip. This is no longer a quick commute measured in minutes or hours. This is longer than the entire duration of a world war. Longer than most university educations. Longer than a presidential term. A traveller who departs Earth toward the closest neighbouring star will spend more time in transit than many people spend at a single job. And Proxima Centauri is not a particularly interesting destination. It is a flare star, prone to violent eruptions of radiation that would strip the atmosphere from any orbiting world. Its lone rocky planet, Proxima Centauri b, orbits within the habitable zone, but faces a bombardment of stellar wind. A light-speed pilgrim who sacrifices 4 years to reach this system finds a dim, volatile star and a world of questionable hospitality. The nearest destination is also one of the least inviting, but let us remain generous. 4 years is manageable. Submarines deploy for months. Antarctic researchers endure years of isolation. Sailors in the age of exploration spent longer at sea. 4 years is a sacrifice, but a comprehensible one. Perhaps the gift of light speed is sufficient after all. It is not. Watch what happens as we push outward. Sirius, the brightest star in Earth's night sky, blazes with 25 times the luminosity of our Sunday ancient Egyptian priests tracked its heliacal rising to predict the annual flooding of the Nile. It dominates the winter sky with a brilliance that makes it seem almost neighbourly. Reaching Sirius at the speed of light requires 8.6 years. A round trip would consume over 17 years of elapsed time. A scientist who departs at age 30 arrives at Sirius at nearly 39. If they turn around immediately, they step back onto Earth at 47. Their children, who were toddlers at departure, are now adults. Nearly 2 decades of birthdays, graduations, first loves, and family milestones occurred, while the traveller chased a single nearby star, Vega, the brilliant blue-white star that once served as Earth's North Pole star and will serve again in approximately 12,000 years, lies 25 light-years from our solar system. A one-way trip at perfect light speed takes a quarter century. The traveller departs as a young adult and arrives solidly into middle age. If they turn back immediately, they return to an Earth that has aged 50 years, half a century. The political map has redrawn itself. Technologies have been invented that did not exist when they left. Cultural references have shifted beyond recognition. The traveller returns as a stranger from a bygone era, clutching data about a star system that nobody remembers commissioning them to visit. Now push further and the numbers begin to swell into something genuinely disturbing. Betelgeuse is the red supergiant that marks the left shoulder of Orion, a dying colossus so bloated that if placed at the centre of our solar system, its surface would engulf the orbits of Mercury, Venus, Earth, and Mars, extending into the asteroid belt. It is one of the most visually striking objects in the night sky, and one of the nearest candidates for a future supernova explosion. Betelgeuse sits approximately 500 to 700 light-years from Earth, with the most recent measurements favouring the nearer end of that range. At the universe's maximum speed, even taking the closer estimate, the journey devours more than 5 centuries, taking the farther estimate, nearly 7. When the traveller arrives, the civilization that launched them existed during the European Middle Ages. The Magna Carta had only recently been signed. The Black Death had not yet swept across Europe. Gunpowder was still a novelty in Western warfare. Every language the traveller spoke has since evolved into something unrecognisable. Every nation they knew has risen, fragmented, and been replaced multiple times. The traveller is not merely old news. They are ancient history. They are an archaeological artefact arriving at a distant star with a cargo manifest written in a dead language. And Betelgeuse is still within our local spiral arm, still within a tiny sliver of the Milky Way, still practically next door by galactic standards. Deneb, the luminous supergiant anchoring the tail of Cygnus the Swan, is one of the most intrinsically brilliant stars visible to the naked eye. It burns with a luminosity estimated between 55,000 and 200,000 times greater than our Sun, depending on its true distance. Visible across astonishing distances, despite sitting roughly 1,500 to 2,500 light-years away, with the most widely accepted modern estimate near the lower end. At light speed, reaching Deneb takes between 15 and 25 centuries, depending on which distance measurement proves correct. The traveller departs and arrives to discover that on Earth, the entirety of Western civilization unfolded during their commute. When they launched, ancient Greece was nearing its classical zenith. Socrates had not yet been sentenced to drink hemlock. Rome had not risen. Christianity, Islam, the Renaissance, the Industrial Revolution, the digital age, every chapter of human cultural development occurred while this single vessel crossed less than 3% of the Milky Way. Let that proportion settle. 3%. 25 centuries of light-speed travel covers 3% of one average galaxy. Eta Carinae, one of the most massive and luminous stars known to astronomers, sits approximately 7,500 light-years away in the Carina Nebula. This stellar monster weighs roughly 100 solar masses and radiates 5 million times the energy of our Sunday. It is so unstable that it erupted in the 19th century in an event called the Great Eruption, briefly becoming the second brightest star in the sky, despite its enormous distance. Eta Carinae is expected to explode as a supernova or even a hypernova within the next few 100,000 years. Reaching Eta Carinae at light speed requires 75 centuries, 7,500 years. When the traveller departs, the earliest known human civilizations have only just begun experimenting with agriculture and permanent settlements. Writing has not been invented, bronze has not been smelted. The traveller arrives at a doomed stellar giant to discover that every empire, every religion, every scientific revolution, every technological transformation in human history occurred after their ship left Earth. The entire accumulated record of civilization, from the first cuneiform tablets to artificial intelligence, represents a story that began after departure and that no one aboard the vessel will ever read. The galactic core, a dense central bulge anchored by a supermassive black hole called Sagittarius A star weighing 4 million solar masses, lies approximately 26,000 light-years from our position in the Orion Arm. At light speed, reaching the centre of our own galaxy requires 26,000 years. A round trip consumes 52,000 years. When the traveller returns, anatomically modern humans have existed for roughly the same duration as the voyage itself. The entirety of civilization, from the oldest known cave paintings to orbital telescopes, fits inside a window shorter than the commute, and crossing the full diameter of the Milky Way, edge to edge, demands 100,000 years, 100 millennia, 1,000 centuries. A span during which ice ages come and go, species evolve and vanish, continents drift measurably, and the entire recorded saga of humanity occupies a slender parenthetical remark near the end. These are the distances within our own galaxy, a single island of stars among trillions. This is the neighbourhood. This is home. Now here is where Einstein's physics introduces a twist that initially appears to rescue the entire enterprise, but ultimately reveals a deeper and more devastating cost. Special relativity, confirmed to extraordinary precision through decades of experimental verification, tells us that time does not pass at the same rate for all observers. The faster an object moves through space, the slower time passes for that object relative to a stationary observer. This effect, called time dilation, is negligible at everyday speeds. A car on a highway, a jet crossing the Atlantic, even the International Space Station orbiting at 17,000 miles per hour. The time dilation at these velocities is real but undetectably small. Atomic clocks aboard GPS satellites must correct for relativistic effects to maintain accuracy, but the corrections amount to fractions of microseconds per day. At velocities approaching the speed of light, however, time dilation becomes dramatic. For a traveller moving at 90% of light speed, time slows by a factor of roughly 2.3. 1 year aboard the ship corresponds to 2.3 years passing on Earth. Significant, but not transformative. At 99% of light speed, the factor climbs to approximately 7. 1 ship year equals 7 Earth years. At 99.9%, the factor reaches roughly 22. At 99.99%, it exceeds 70. 1 year of the traveller's life corresponds to 70 years of history back home. At 99.9999% of light speed, the dilation factor surpasses 700. The traveller ages 1 year, Earth ages 7 centuries. And at the theoretical limit of perfect light speed, which no massive object can actually reach but which we are generously granting, time dilation becomes infinite. For a photon travelling at exactly light speed, no time passes at all. The journey from emission to absorption, whether it crosses a room or the entire observable universe, registers as instantaneous from the photon's own frame of reference. This sounds like the ultimate loophole, a cheat code hidden in the laws of physics. If time dilation compresses the traveller's experience, then even journeys spanning thousands of light years might feel like months or years to the person inside the ship. The traveller could cross the galaxy and barely age. They could reach Andromeda and feel as though a long afternoon had passed. But time dilation does not erase distance, it transfers the cost from one clock to another. Consider a concrete scenario. A traveller accelerates to 99.99% of light speed and heads toward a star system 1,000 light-years away. Due to time dilation and the related effect called length contraction, the journey from the traveller's perspective takes roughly 14 years. They arrive, survey the system, record their findings, and turn the ship around. Another 14 years of subjective travel carries them back to Earth's coordinates. The traveller has aged 28 years. They feel healthy. They feel rested. They feel as though they have completed a long but manageable expedition. But when they step off the ship, Earth has experienced over 2,000 years. Every person they knew is dead. Not recently dead, dead for centuries. Their language has mutated beyond comprehension. Their nation has dissolved and reformed and dissolved again multiple times. Technologies they cannot fathom permeate daily life. The music, the art, the social structures, the governing systems, every facet of the world they departed bears no resemblance to what they returned to. The traveller is a living fossil, a biological relic from an era as remote as the Roman Republic is to us today. Every piece of this has been measured. Atomic clocks flown on aircraft tick at different rates than ground-based clocks, matching Einstein's predictions with stunning precision. Particle accelerators observe unstable particles lasting far longer than their resting lifetimes because time dilation stretches their decay clocks. Muons generated by cosmic rays in the upper atmosphere reach Earth's surface in quantities that would be impossible without relativistic time effects. The science is unambiguous, and it means that light-speed travel does not conquer interstellar distances. It transforms them from a spatial problem into a temporal catastrophe. The traveller can go. They cannot come home. Not to the world they left. Not to the people who launched them. Not to the civilization that built their ship. From the traveller's compressed frame, the stars are reachable. Proxima Centauri passes in subjective moments at near light speed. Sirius flickers by. Vega vanishes into the rearview. The galaxy scrolls past like a cosmic time-lapse. But in the frame of everyone else, every star the traveller visits costs years, centuries, or millennia of real time. The traveller buys their cosmic tour with the currency of everything they knew. Every light year crossed is a year of Earth time spent. Every star visited is a decade, a century, an epoch irretrievably consumed. Time dilation does not cheat the universe. It lets the traveller be unconscious of the price while reality pays it in full. There is a further complication that deserves attention. Everything discussed so far assumes instantaneous acceleration to light speed. In reality, even granting our generous assumption, a human body cannot survive sudden acceleration to light speed. The G-forces would liquefy every cell. A more realistic scenario involves gradual acceleration at a rate comfortable for human passengers, perhaps 1 g, equivalent to Earth's surface gravity. At 1 g of sustained acceleration, a ship reaches 99% of light speed in approximately 1 year of ship time. Reaching 99.9% takes a bit longer. The ship would accelerate through the first half of the journey and decelerate through the second half, arriving at the destination at rest. Under this acceleration profile, a trip to Proxima Centauri at 1G takes roughly 3.6 years of ship time. A trip to Vega takes approximately 6.6 years of ship time. A trip to the center of the galaxy takes roughly 20 years of ship time. And a trip across the full 100,000 light-year diameter of the Milky Way takes approximately 24 years of ship time. 24 years. From the traveler's perspective, crossing the entire galaxy takes roughly the same amount of time as raising a child from birth to adulthood. This sounds astonishing. It sounds almost practical. But the external clock tells a savagely different story. While the traveler ages 24 years, the galaxy itself ages 100,000 years. The traveler steps off the ship on the far side of the Milky Way and looks back toward Earth. The light arriving from Earth's direction shows conditions as they existed 100,000 years ago. The signal confirming their arrival will not reach Earth for another 100,000 years. The round-trip communication time is 200,000 years. The traveler tries to send a message home. A simple confirmation. I arrived. The far side of the galaxy is beautiful. That message, traveling at the speed of light, crosses the Milky Way and arrives at Earth's coordinates 100,000 years later. If anyone receives it, if any descendant civilization remembers to listen, they hear the voice of a being from so deep in their past that the message might as well have been carved on a cave wall. The traveler is not merely distant, they are chronologically alien, separated from home by a temporal gulf that renders every shared reference point extinct. Any report they send, any discovery they make, any warning or celebration or simple greeting they transmit arrives at a destination where no one remembers them, where their language is extinct, where the very concept of their mission has been lost to deep time. They have traded 24 years of personal life for permanent exile from their entire species. This is the transaction that light-speed travel demands at galactic scales. The traveler's subjective compression of time is real and measurable, but the external time cost is equally real and equally measurable. Both clocks tell the truth, both realities coexist. The traveler genuinely ages only 24 years. The universe genuinely ages 100,000 years. No paradox, no contradiction. Just a brutal asymmetry written into the structure of space-time itself. And we have not yet left the galaxy. Every star we have visited, every journey we have timed, every relativistic calculation we have run, concerns destinations within a single spiral galaxy among an estimated 2 trillion in the observable universe. The Milky Way, with its 400 billion stars spread across 100,000 light-years, is one cosmic city in a universe containing trillions of cities, spread across 93 billion light-years of observable space. Every number we have calculated so far, every century and millennium of travel time, applies to our immediate neighbourhood, our block, our street. The distance to the nearest major galaxy dwarfs everything we have confronted. The Andromeda Galaxy, our closest large neighbour, lies 2.5 million light-years away. The galaxy clusters and superclusters that form the scaffolding of cosmic structure sit at distances measured in tens of millions and hundreds of millions of light-years. The most distant objects we can observe emitted their light over 13 billion years ago from regions that now sit more than 46 billion light-years away due to the expansion of space. Light speed handles the solar system in hours. It handles nearby stars in years. It handles the galaxy in millennia that crush civilizations under the weight of elapsed time. Against the full scale of the cosmos, it has not yet even begun to be tested. And when it is tested against intergalactic distances, it breaks completely. We granted ourselves the impossible and tested it against individual stars. The results were sobering. Even at the universe's absolute speed limit, reaching nearby stellar neighbours costs years. Reaching prominent stars across our spiral arm costs centuries or millennia. Crossing the full diameter of the Milky Way demands 100,000 years of external time, during which civilizations rise, flourish, collapse, and are forgotten while the traveller's clock ticks through mere decades. But every destination we visited belongs to a single galaxy. One island of 400 billion stars in a cosmos containing trillions of such islands. Now we leave the Milky Way behind and confront what waits between the galaxies. This is where light speed does not merely struggle. This is where it begins to fail in absolute terms. Before we leap into intergalactic space, we need to appreciate one final dimension of galactic travel that we have only touched upon. The Milky Way is not just wide, it is deep with structure. Our solar system orbits the galactic center at a distance of roughly 26,000 light-years, embedded in a minor spur branching off the Orion Arm. But the galaxy contains regions of extraordinary density and violence that light-speed travel would need to navigate or circumvent. The galactic core is a maelstrom. Within the central few light-years, stars orbit Sagittarius A star at velocities exceeding 10 million miles per hour. Radiation fields near the center would sterilize any unshielded vessel. Dense molecular clouds hundreds of light-years across block direct paths through the inner galaxy. A light-speed traveler attempting to cross the Milky Way does not fly through open vacuum. They thread a labyrinth of gravitational hazards, radiation zones, and obscuring dust lanes that complicate any straight-line transit. The galaxy also rotates differentially. Stars closer to the center orbit faster than stars in the outskirts. Our solar system completes one galactic orbit approximately every 230 million years, a period sometimes called a cosmic year. During the 100,000 years required for a light-speed crossing of the galaxy, the spiral arms rotate measurably. The destination a traveler aimed for at departure has physically moved by the time they arrive. Not by vast amounts, but enough to matter for precision navigation across tens of thousands of light-years. The galaxy is not a frozen target. It is a spinning wheel, and every point on it shifts during any transit measured in millennia. None of these complications are deal-breakers for a hypothetical light-speed civilization. They are simply reminders that even within our galaxy, travel at the cosmic maximum is not the clean, effortless glide that intuition suggests. Distances are vast, timescales are crushing, and the medium through which the traveller moves is dynamic, hazardous, and structurally complex. But all of this pales against what lies beyond the galactic edge. Step outside the Milky Way, and you enter a void that redefines the concept of emptiness. Intergalactic space is the loneliest environment in the known universe. The average density of matter between galaxies drops to roughly 1 atom per cubic meter. For comparison, the best laboratory vacuum chambers on Earth contain approximately 25 billion molecules per cubic centimeter. Intergalactic space is emptier than anything human technology can create by factors that defy easy description. It is not merely vacant. It is a near-perfect nothing, stretching across distances measured in millions of light-years. Temperature in this void hovers near the cosmic baseline. The remnant warmth of the Big Bang stretched thin by 13.8 billion years of expansion, a few degrees above absolute zero. Cold enough that molecular motion nearly ceases. Cold enough that any unprotected structure would radiate its thermal energy into the void and approach equilibrium with the background radiation of the universe itself. This is the medium a light-speed traveller must cross to reach the next galaxy, not a brief gap between neighbouring houses on the same street. An oceanic expanse of almost perfect vacuum, lightless and structureless, extending for millions of light-years in every direction. Even at the cosmic speed limit, the crossing takes longer than the entire evolutionary history of our species. Into this emptiness, aim for Andromeda. The Andromeda Galaxy, also catalogued as Messier 31, is the nearest large spiral galaxy to the Milky Way. Visible to the naked eye on clear autumn nights as a faint, elongated smudge in the constellation that bears its name, Andromeda has been observed by humans for over 1,000 years. The Persian astronomer Abd al-Rahman al-Sufi described it in the 10th century as a small cloud. For most of recorded history, astronomers assumed it was a nebula within our own galaxy, a cloud of gas and dust rather than a separate cosmic structure. That assumption shattered in 1924 when Edwin Hubble identified individual Cepheid variable stars within Andromeda and calculated their distances. The results stunned the scientific world. Andromeda was not a local gas cloud. It was an entirely separate galaxy, far beyond the boundaries of the Milky Way. The universe, in a single measurement, expanded from one galaxy to at least two. Subsequent observations revealed billions more. Andromeda contains approximately 1 trillion stars, roughly 2.5 times the stellar population of the Milky Way. Its disk stretches about 220,000 light-years across, more than double the diameter of our galaxy. It is more massive, more luminous, and more structurally complex than our cosmic home. If the Milky Way is a mid-sized city, Andromeda is the sprawling metropolis visible on the horizon. The distance between us measures 2.5 million light-years. 2,500,000 light-years. At the cosmic speed limit, without pause, without deviation, without any obstacle, the crossing requires 2.5 million years of external elapsed time. Sit with that number. 2.5 million years. When the light now arriving from Andromeda began its journey toward Earth, the genus Homo was just emerging. Homo habilis, among the earliest members of our lineage, was beginning to chip crude stone tools in the Rift Valley of East Africa. Bipedalism was established, but brain volumes were a fraction of modern human capacity. Language as we understand it did not exist. Fire had not been mastered. The cognitive distance between those early hominids and the species that would eventually build telescopes and contemplate galactic travel is almost as vast as the physical distance the light traversed. A light-speed traveller departing today toward Andromeda would arrive after 2.5 million years have elapsed on Earth. What survives of humanity across such a duration? The fossil record offers a grim benchmark. The average lifespan of a mammalian species is roughly 1 to 2 million years. Homo sapiens has existed for approximately 300,000 years. Even if our species proves unusually durable, 2.5 million years vastly exceeds the typical evolutionary persistence of any complex organism. The traveller arrives at Andromeda to discover that the species which launched them may no longer exist in any recognizable form. Evolution does not pause. Selection pressures do not relent. 2.5 million years of genetic drift, environmental change, and adaptive radiation would transform whatever descendants survive into something biologically distinct from the beings who built the ship. And this assumes the civilization endures at all. Extinction events are not hypothetical. They are documented features of Earth's biological history. 5 major mass extinctions punctuate the last 540 million years. Asteroid impacts, supervolcanic eruptions, climate shifts, ocean chemistry changes. The mechanisms vary, but the pattern is consistent. Complex life on Earth faces periodic existential crises, separated by tens to hundreds of millions of years. A civilization spanning 2.5 million years must survive multiple potential extinction-level threats. History offers no precedent for this kind of endurance. Time dilation, once again, offers its deceptive compression. A traveller accelerating at 1 g of sustained thrust toward Andromeda would experience approximately 28 years of ship time for the journey. 28 years, less than a standard career. The traveller departs in their 30s and arrives in their late 50s, physiologically speaking. From inside the ship, the trip feels long but survivable. Tedious, perhaps. Lonely, certainly, but physically manageable. Outside the ship, 2.5 million years grind past. Glaciers advance and retreat across continents. River systems carve new valleys. Tectonic plates shift measurably. Mountain ranges erode and new ones rise. The constellations visible from Earth's surface rearrange themselves as nearby stars follow their own orbital paths around the galactic center. The night sky the traveller memorized before departure no longer exists. If the traveller wishes to report their findings, they face a communication delay that compounds the absurdity. A signal sent from Andromeda at the speed of light requires 2.5 million years to reach Earth. The round-trip information exchange, question and answer, report and acknowledgement, spans 5 million years. 5 million years. The entire genus Homo, from the earliest tool-using hominids to every human being alive today, fits inside that communication window with room to spare. The traveller transmits their discoveries into a void so deep in time that the very concept of a recipient becomes meaningless. Their report is not late. It is archaeologically ancient before it arrives. A message in a bottle tossed into an ocean where the shoreline will have eroded into a different continent before the bottle washes up. No organisational structure in human history has maintained coherence across such timescales. No language has survived unchanged for even a tenth of that duration. No institution, no religion, no government, no cultural tradition has persisted for 5 million years. The traveller's transmission would arrive as an indecipherable signal from a forgotten epoch, assuming any receiver still operates, assuming anyone remembers to listen, assuming the concept of listening still carries meaning for whatever intelligence inhabits the Earth of that distant future. Consider what Earth looks like after 5 million years of unattended evolution. The continents have shifted. The Mediterranean Sea may have closed entirely as Africa continues its northward collision with Europe, raising new mountain ranges where open water once existed. The East African Rift Valley has widened, potentially splitting the continent and creating a new ocean basin. Coastlines have been redrawn by tectonic forces, and sea level changes driven by cycles of glaciation and warming. The animals inhabiting these transformed landscapes bear little resemblance to anything alive today. 5 million years ago, the ancestors of modern elephants looked nothing like modern elephants. The ancestors of modern horses were small, multi-toed browsers. 5 million years of evolution transforms families, reshuffles ecosystems, and drives entire lineages to extinction while elevating others to dominance. Whatever walks on Earth when the traveller's report arrives from Andromeda inhabits a biological world as foreign to us as the Pliocene savanna would be to a modern city dweller. The traveller did not merely leave home. They left a planet, a biosphere, and a geological era that will have been replaced wholesale by the time their first word reaches back across the void. This is the intergalactic communication problem, and it applies universally. Any two galaxies separated by millions of light years face the same barrier. Even if both harbour advanced civilizations, even if both achieve perfect light-speed signalling, the exchange of a single message and reply requires millions of years. Meaningful dialogue, the iterative exchange of ideas that drives collaborative progress, becomes physically impossible across intergalactic distances. Each galaxy is a conversational island, capable of shouting into the void but unable to sustain anything resembling a discussion. Now widen the aperture beyond Andromeda. The Milky Way and Andromeda are the two dominant members of a gravitational family called the Local Group. This collection contains more than 50 galaxies bound together by mutual gravitational attraction within a volume spanning roughly 10 million light-years. Most members are dwarf galaxies, small systems containing a few billion stars each. The Large Magellanic Cloud sits 160,000 light-years away. The Small Magellanic Cloud orbits at 200,000 light-years. Dozens of smaller dwarfs, the Sagittarius Dwarf Elliptical, the Draco Dwarf, the Ursa Minor Dwarf, populate the surrounding space like satellites orbiting a gravitational hub. These satellite galaxies are not merely neighbours, they are captives. The Milky Way's gravitational influence extends far beyond its visible disk, reaching out through an enormous dark matter halo that envelops the smaller systems and dictates their orbits. The Sagittarius Dwarf is currently being torn apart by tidal forces, its stars stripped away and scattered into long streams that wrap around our galaxy like evidence at a crime scene. The Large Magellanic Cloud, once thought to be a permanent companion, may itself be on its first infall toward the Milky Way, destined to be consumed within a few billion years. Our galaxy is not a passive island. It is a gravitational predator, steadily devouring its smaller companions. At light speed, the most distant members of the local group require roughly 10 million years to reach. The full extent of our gravitational family demands a transit time that exceeds the entire duration of the Miocene epoch on Earth, the period during which the ancestors of modern apes first diverged from earlier primate lineages. Reaching the edge of our own cosmic neighborhood, the modest collection of galaxies we can call our own takes longer than the evolutionary journey from early apes to modern humans. The local group is often treated as a footnote in cosmic geography, a modest cluster of galaxies barely worth mentioning compared to the grand superclusters and filaments of the cosmic web. But for a light-speed civilization, the local group represents something far more significant. It represents the outer boundary of practical existence. Every galaxy within the local group is gravitationally bound to every other member. The mutual attraction between these 50-odd systems is strong enough to resist the expansion of space that carries more distant structures away from us. The local group will remain intact as a gravitational unit for the foreseeable cosmic future, its members orbiting, colliding, and merging over billions of years while the rest of the universe recedes. This means the local group is not just a neighborhood, it is a lifeboat, a gravitationally sealed vessel carrying a finite cargo of galaxies through an expanding ocean. Everything within it can theoretically be reached at light speed, given sufficient patience and willingness to sacrifice connection to home. Everything beyond it is subject to cosmic expansion, recession velocities, and the accelerating influence of dark energy. The boundary of the local group is not merely a line on an astronomer's chart. It is the threshold between the reachable and the increasingly unreachable. Between the cosmos, a light-speed civilization could explore across millions of years, and the cosmos that is actively pulling itself away from their grasp. And even within this lifeboat, the scale is punishing. The local group spans 10 million light-years. Crossing it at light speed takes 10 million years. A signal sent from one edge to the other and back requires 20 million years for a round trip. Coordinating any activity across the full extent of the local group demands patience measured in geological epochs. The lifeboat is vast enough to contain entire evolutionary histories within a single communication cycle. Beyond the local group, the cosmos organizes itself into increasingly massive structures. Galaxy groups cluster into galaxy clusters. Clusters assemble into superclusters. Superclusters connect through filaments of dark matter and gas to form the cosmic web, a vast three-dimensional network that represents the largest structural pattern in the observable universe. The nearest major galaxy cluster beyond our local group is the Virgo cluster, a congregation of over 1,300 galaxies centered approximately 54 million light-years from Earth. The Virgo cluster is a gravitational heavyweight, massive enough to influence the motion of galaxies across hundreds of millions of light-years. Our own local group is falling toward Virgo at roughly 400 kilometers per second, drawn by its immense gravitational pull. At light speed, reaching the Virgo cluster requires 54 million years. To grasp what this means for the traveller's homeworld, 54 million years ago, the dinosaurs had been extinct for approximately 12 million years. Early primates were small nocturnal creatures scurrying through tropical forests. The Indian subcontinent was still actively colliding with the Asian plate, beginning the uplift that would create the Himalayas. The entire evolutionary arc from those tiny tree-dwelling mammals to a technological civilization capable of launching interstellar vessels occurred within a span shorter than the transit time to Virgo. Time dilation at extreme velocities compresses this for the traveller. At 99.999999% of light speed, the dilation factor approaches 7,000. The subjective journey to Virgo would last approximately 7,700 years, still staggering, longer than the entire history of urban civilization on Earth, longer than the span from the first Sumerian city-states to the present day. The traveller ages through millennia of subjective experience, while 54 million years elapse on every clock in the external universe. And what awaits the traveller at Virgo? A cosmic metropolis unlike anything in our quiet local group. The Virgo cluster contains over 1,300 galaxies packed into a volume roughly 15 million light-years across. At its heart sits Messier 87, a supergiant elliptical galaxy containing several trillion stars and harbouring one of the most massive black holes ever observed, a monster weighing between 5 and 6.5 billion solar masses. The cluster is flooded with superheated intracluster gas reaching temperatures of tens of millions of degrees, glowing in X-ray wavelengths, containing more mass than all the cluster's visible galaxies combined. Galaxies within Virgo hurtle past each other at speeds exceeding 3 million miles per hour, their trajectories governed by enormous reservoirs of dark matter that outweigh the luminous matter by a factor of 10. The Virgo cluster is violent, dense, and radically different from the serene gravitational backwater of the local group. It is exactly the kind of structure a civilization would want to study, and it costs 54 million years to reach. If the traveller attempts to send their findings home, the signal crawls back across 54 million light-years at the speed of light. The round-trip communication time spans 108 million years. When the traveller's report departs from Virgo, dinosaurs have already been extinct for 12 million years. When that same report arrives at Earth, the planet has aged another 54 million years on top of the 54 million that elapsed during the outbound journey. Whatever receives the signal exists 108 million years after the mission launched. The concept of a mission report implies a recipient who commissioned the mission. After 108 million years, that implication becomes absurd. The traveller's data arrives at a world that has experienced multiple mass extinction events, complete biosphere turnovers, and tectonic reconfigurations since the day the ship departed. The report is not late. It is fossilized before it arrives. Push further to the Coma cluster, and the absurdity deepens. Coma is one of the densest and most well-studied galaxy clusters in the observable universe, containing over 1,000 major galaxies dominated by 2 supergiant ellipticals at its core. The cluster is bound together by dark matter so massive that the visible galaxies account for less than 5% of its total gravitational budget. The intracluster gas burns even hotter than Virgo's, reaching 100 million degrees in some regions. Coma is a furnace of gravitational violence, a cosmic pressure cooker where galaxies are stripped of their gas, reshaped by tidal forces, and transformed from vibrant spirals into passive ellipticals over billions of years. Reaching Coma means crossing 320 million light-years. A round-trip communication spans 640 million years. The traveller who sends a greeting from Coma waits for a reply that arrives after a duration exceeding the entire Phanerozoic eon. Every animal that has ever lived on Earth fits inside that waiting period. Push further. The Coma cluster, a dense knot of galaxies bound together by dark matter and superheated intracluster gas, lies roughly 320 million light-years from Earth. At light speed, the journey requires 320 million years. When the traveller arrives, the external Earth exists in what would currently be the late Carboniferous period. Vast coal swamps cover the continents. Amphibians dominate terrestrial ecosystems. The first reptiles are only beginning to diversify. Insects have evolved flight, but vertebrates have not. The entire age of dinosaurs, the rise and extinction of the great reptiles, the emergence of mammals, the evolution of primates and eventually humans, all of this occurs while a single vessel crosses the distance to one galaxy cluster. The Shapley supercluster, one of the most massive gravitational concentrations in our observable region, sits approximately 650 million light-years away. A light-speed journey to Shapley consumes 650 million years. At departure, complex multicellular life on Earth was in its earliest stages. The Ediacaran biota, those strange soft-bodied organisms preserved in ancient seafloor sediments, had not yet appeared. The traveller arrives at a cosmic superstructure to find that the entire Phanerozoic eon, every chapter of visible animal life from trilobites to elephants, transpired during the commute. And these are merely the structures close enough to have names and detailed measurements. Beyond Shapley, the universe continues without interruption. Galaxy clusters and superclusters extend outward in every direction, populating the cosmic web to distances of billions of light-years. At 2 billion light-years, the transit time exceeds the entire history of complex multicellular life on Earth. At 5 billion light-years, the journey consumes more time than the Sun has existed. At 10 billion light-years, the traveler would arrive after a duration approaching the current age of the universe itself. The ship that departed from a young Earth would arrive at a destination where the universe has roughly doubled in age since launch. At these distances, the concept of travel begins to dissolve entirely. A journey that takes 10 billion years is not travel in any meaningful sense. It is existence on a cosmic timescale, a process so slow and so vast that the distinction between moving and simply waiting for the universe to age becomes academic. The traveller is not exploring, they are enduring. They are persisting through spans of time during which stars are born, burn through their entire fuel supply, and die as cold remnants. Multiple generations of stellar evolution occur during a single voyage. The traveller crosses space that has been fundamentally transformed by cosmic processes between departure and arrival. These distances expose the fundamental asymmetry between light speed and cosmic structure. Light speed feels infinite from a human perspective. It crosses the solar system in hours. It reaches nearby stars in years. But the universe distributed its galaxies at separations measured in millions and billions of light years. The ratio between our speed and these distances is so extreme that light speed travel becomes functionally equivalent to geological time travel. You move through space, but you also move through eons. And the distances to these clusters represent merely the intermediate rungs of the cosmic ladder. The observable universe extends 46.5 billion light-years in every direction. Galaxy clusters and superclusters populate this volume in their hundreds of thousands, connected by filaments of the cosmic web into a structure so vast that individual galaxies are invisible at the largest scales, like atoms within a cathedral. The most distant galaxies we can detect emitted their light when the universe was less than 500 million years old. Their photons have been travelling for over 13 billion years. The objects that emitted them now lie at comoving distances exceeding 30 billion light-years, carried to these extreme separations by the cumulative expansion of space across cosmic history. These numbers shatter the intuition that light speed conquers cosmic distances. At every scale beyond the local group, the transit times exceed not just the duration of civilizations, but the duration of entire geological periods, entire evolutionary epochs, entire chapters of planetary history. A light-speed traveller to a distant galaxy cluster is not merely separated from home by distance. They are separated by time on a scale that renders the concept of home meaningless. There is nothing to return to. There is no continuity between departure and arrival. The traveller and their origin exist in different biological eras. But there is a further complication that transforms this already devastating picture into something categorically worse. The galaxies beyond our local group are not stationary targets. They are moving away from us, and the farther away they are, the faster they recede. This recession is not motion through space in the conventional sense. Galaxies are not rocketing away like shrapnel from an explosion. Instead, the fabric of space itself is expanding. The distance between any two unbound points in the universe increases over time as new space appears between them. This expansion was first observed by Edwin Hubble in 1929 and has been confirmed and refined through nearly a century of subsequent measurement. Hubble's law describes the relationship precisely. The recession velocity of a distant galaxy is proportional to its distance. For every megaparsec of separation, approximately 3.26 million light-years, galaxies recede at roughly 67 to 74 kilometers per second, depending on the measurement method used. This rate, called the Hubble parameter, is small at local scales but compounds relentlessly with distance. At the distance of the Virgo cluster, 54 million light-years, the recession velocity is approximately 1,100 kilometers per second. Fast by terrestrial standards, but tiny compared to light speed. The expansion barely affects a light-speed traveler at this range. At 320 million light-years, the distance to the Coma cluster, recession velocity climbs to roughly 7,000 kilometers per second. Still a small fraction of light speed, but no longer negligible. Space is stretching between the traveler and the destination at a measurable rate. The target is moving away during the journey. The effective travel time increases beyond the simple distance divided by speed calculation. At 1 billion light-years, recession velocity reaches approximately 22,000 kilometers per second. At 5 billion light-years, roughly 110,000 kilometers per second. The expansion of intervening space now adds meaningful distance during transit. A light-speed traveler aimed at a galaxy 5 billion light-years away does not simply cross 5 billion light-years. They cross 5 billion light-years, plus the additional space that appears between them and the target during the billions of years the journey takes. The actual distance traversed exceeds the initial measurement. This effect accelerates with distance. The farther the target, the faster it recedes, the more new space appears during transit, the longer the journey actually takes compared to the naive calculation. At sufficiently large distances, this compounding overwhelms even light speed. The threshold at which recession velocity equals the speed of light currently sits at approximately 14.4 billion light-years, a boundary called the Hubble radius. Beyond this distance, space expands faster than photons can cross it. A light-speed traveler aimed at a galaxy beyond the Hubble radius faces a destination that recedes at or above the cosmic speed limit. The traveler moves at maximum velocity through local space while the space ahead of them stretches faster than they can traverse it. No propulsion system can overcome this. No engineering breakthrough or surge of willpower or leap of technological ambition can alter the outcome. It is a structural feature of the universe itself. Space grows. The growth rate increases with distance. Beyond a critical threshold, no velocity, not even the maximum velocity permitted by the laws of physics, can overcome the rate at which new space appears between origin and destination. And there is one additional factor that makes this problem not merely static, but actively worsening. The expansion of space is accelerating. In 1998, two independent teams of astronomers studying distant Type Ia supernovae discovered that the universe's expansion rate is not constant. It is increasing over time. Distant supernovae appeared dimmer than expected, indicating they were farther away than a constant expansion rate would predict. The universe is not just expanding. It is expanding faster and faster. The force driving this acceleration is called dark energy, a form of energy inherent to the vacuum of space that exerts a repulsive gravitational effect. Dark energy constitutes approximately 68% of the total energy content of the universe. Unlike matter, which dilutes as space expands, dark energy maintains a constant density. As the universe grows, the total amount of dark energy increases proportionally. More space means more dark energy, means faster expansion, means more space. The cycle feeds itself. This accelerating expansion means that the Hubble radius is not fixed, the threshold beyond which galaxies recede faster than light shifts over cosmic time. More crucially, it means that galaxies currently within reach are being carried toward that threshold. Objects that a light-speed traveler could theoretically reach today will become unreachable tomorrow, swept beyond the cosmic speed limit by the accelerating tide of expansion. The local group resists this tide. Gravitational binding within our cluster of galaxies is strong enough to counteract cosmic expansion. The Milky Way and Andromeda will continue their gravitational dance regardless of what happens to the broader cosmos. Our immediate neighborhood remains intact, but everything beyond the local group is being carried away. The Virgo cluster recedes. The Coma cluster recedes faster. The great superclusters that mark the nodes of the cosmic web recede faster still. Each megaparsec of distance adds another increment of recession velocity, and dark energy ensures that each increment grows larger with every passing billion years. For a light-speed traveler, the universe beyond the local group is a landscape of retreating targets. Some are receding slowly enough that a sufficiently patient voyage could reach them, though the transit times already exceed geological epochs. Others are receding so quickly that the traveler would fall behind despite moving at the cosmic maximum, and the boundary between reachable and unreachable shifts inward over time as acceleration pushes more and more galaxies beyond the speed of light recession threshold. This is the fundamental asymmetry of our cosmos. The universe built structures at distances that exceed its own speed limit. Then it arranged for those distances to grow faster over time. Light speed, the absolute ceiling of physical velocity, is not merely insufficient. It is becoming more insufficient with every passing second as dark energy stretches the cosmic fabric and pushes the distant universe further beyond any possible reach. What comes next is the full reckoning with this expanding trap. The precise calculation of how much of the observable universe remains accessible to a light-speed traveler. The answer is far smaller than most people imagine, and it is shrinking. We have now crossed the Milky Way and ventured beyond it into intergalactic distances that shatter the utility of light-speed travel. We confronted transit times measured in millions and hundreds of millions of years. We introduced the expansion of space and the recession of distant galaxies. We established that beyond a certain distance, galaxies recede faster than light, not through motion, but through the growth of space itself. But we left a critical question unanswered. Exactly how much of the universe can a light-speed traveler actually reach? The answer requires understanding a boundary more fundamental than the Hubble radius, a boundary that defines the absolute edge of cosmic accessibility for any civilization, anywhere, at any point in the future. That boundary is the cosmic event horizon, and what it reveals about our situation is far more restrictive than anything we have yet encountered. The Hubble radius, introduced at the end of Part 2, marks the distance at which recession velocity currently equals the speed of light. It sits at approximately 14.4 billion light-years. Beyond this distance, galaxies recede superluminally right now, but the Hubble radius is not a fixed wall. It is a snapshot of current conditions. As the universe evolves, the Hubble radius changes. And crucially, the Hubble radius does not represent the true limit of reachability. A photon emitted today toward a galaxy just beyond the Hubble radius is not immediately doomed. The photon enters a region of space that is currently receding faster than light, but the Hubble radius itself grows over time because the expansion rate changes. If the Hubble radius expands to encompass the photon's current position, the photon finds itself back in subluminal territory, able to make forward progress again. This subtlety means that some galaxies currently receding faster than light can still be reached by a light-speed signal or traveler, given enough time. The photon struggles initially, swept backward by the expansion of local space, but if conditions evolve favorably, it eventually gains ground and reaches the target. This is not intuitive. It sounds like catching a bus that is pulling away faster than you can run, but cosmic expansion is not uniform across all time. The relationship between the Hubble radius and the photon's position shifts over cosmic epochs, sometimes allowing the photon to eventually overtake the expansion at a given distance. However, this reprieve has a firm limit, and that limit is the cosmic event horizon. The cosmic event horizon represents the absolute maximum distance from which a signal sent at the speed of light right now could ever reach us, or equivalently, the farthest point we could ever reach if we departed at light speed right now. It accounts not just for the current expansion rate, but for the entire future evolution of expansion, integrated forward across infinite time. It asks a comprehensive question. Given that expansion is accelerating and will continue to accelerate, given that dark energy maintains constant density as space grows, given the full trajectory of cosmic evolution from this moment onward, how far can light ultimately travel? The answer, under current cosmological parameters, places the cosmic event horizon at approximately 16.5 billion light-years in terms of current proper distance. This is the farthest moving distance a photon emitted today from Earth could ever reach. Even given an infinite amount of time to travel, this number is larger than the Hubble radius because, as described, photons can temporarily lose ground to expansion and later recover. But it is devastatingly smaller than the observable universe. The observable universe extends 46.5 billion light-years in every direction, encompassing a sphere of approximately 93 billion light-years in diameter. The cosmic event horizon extends only 16.5 billion light-years. The reachable volume is a small fraction of the observable volume. Let us quantify this precisely. Volume scales with the cube of the radius. The observable universe has a co-moving radius of 46.5 billion light-years. The cosmic event horizon has a co-moving radius of approximately 16.5 billion light-years. The ratio of volumes is the cube of the ratio of radii. 16.5 divided by 46.5 is approximately 0.355. Cubing this gives roughly 0.045, or about 4.5%. Roughly 4 to 6% of the observable universe lies within our cosmic event horizon. The precise figure depends on the cosmological parameters used, particularly the dark energy equation of state and the exact value of the Hubble parameter, both of which carry measurement uncertainties. But the order of magnitude is consistent across mainstream calculations. Approximately 94 to 96% of the galaxies we can currently observe are already beyond our cosmic event horizon. Pause on that number. 94%. Look up at the night sky on a clear evening and imagine every galaxy that telescopes have ever photographed. Every spiral, every elliptical, every irregular dwarf, every luminous quasar blazing at the edge of detectability. Now arrays 94 out of every 100. Remove them not just from sight but from possibility. They are not hidden. They are not waiting to be visited. They are receding beyond the reach of any signal, any spacecraft, any physical influence that could ever depart from Earth, even at the maximum velocity the universe permits. The remaining 6% is everything. Every galaxy a light-speed civilization could theoretically interact with across the entire remaining lifespan of the cosmos. Every star system that could ever receive a transmission from Earth. Every world that could ever be visited, colonized, studied, or contacted by any means consistent with the laws of physics. To visualize this, imagine a vast library containing 2 trillion books. Each book represents a galaxy, filled with chapters of stellar systems and pages of individual worlds. You are permitted to read 6% of this library. The rest of the shelves are locked behind glass that grows thicker with every passing year. You can see the spines of those unreachable volumes. You can read their titles through the glass. You can even study the faded text on their covers using sufficiently powerful magnifying instruments. But you can never open them. You can never read what is inside. And the glass is slowly frosting over, obscuring even the titles, until eventually you will not know those books exist at all. 6% still represents an enormous inheritance. 120 billion galaxies is not a small number, each containing billions of stars, each star potentially hosting worlds, each world representing a unique experiment in planetary formation. The reachable cosmos is staggeringly rich by any terrestrial standard, but it is a sliver of what exists. A thin, bright ribbon of accessibility surrounded by an ocean of permanently unreachable space that dwarfs it by a factor of nearly 20 to 1. They are visible because their ancient light had time to reach us from earlier epochs when they were closer, but their current positions place them permanently beyond the reach of any signal or traveller departing Earth today, even at the speed of light, even given infinite time. Let that proportion crystallize. We can see roughly 2 trillion galaxies. We can reach perhaps 120 billion of them. The remaining 1,880 billion galaxies exist in our telescopes, but not in our future. They are ghosts of light. Cosmic postcards from locations we will never visit, depicting conditions that no longer exist, sent by structures that have long since evolved beyond recognition, and the situation is deteriorating. Because expansion is accelerating, the cosmic event horizon is not static. It is shrinking in moving coordinates. Galaxies that currently lie just inside the event horizon will cross beyond it in the coming billions of years, carried outward by the accelerating expansion of space. The reachable fraction of the universe decreases with every passing epoch. A civilization that delays its departure loses access to destinations that were available yesterday. The cosmos is not merely vast, it is actively closing its doors. To understand why acceleration produces this shrinking horizon, consider what dark energy does to the expansion rate over time. In a universe without dark energy, expansion would gradually decelerate as the gravitational attraction of matter slows the outward momentum from the Big Bang. In such a universe, the cosmic event horizon would be much larger, potentially infinite. A photon emitted today would always eventually reach any galaxy, no matter how distant, because the expansion rate would continuously decrease, allowing light to gain ground over cosmic time. Dark energy reverses this dynamic. Instead of decelerating, expansion accelerates. The rate at which space stretches increases over time. This means that a photon emitted today faces not just current expansion, but an ever-worsening expansion rate in the future. The space ahead of the photon stretches faster and faster. At a certain distance, the cumulative future expansion exceeds the photon's ability to make progress. No matter how long it travels, the photon runs forever but falls infinitely behind. The cosmic event horizon marks exactly this distance. In a dark energy-dominated universe, which ours became approximately 5 billion years ago, the cosmic event horizon converges to a finite value and then slowly contracts as acceleration intensifies. Every billion years that passes, the horizon creeps inward. Galaxies that were reachable a billion years ago are no longer reachable today. Galaxies that are marginally reachable today will become unreachable within a few billion years. This creates a countdown that no civilization can escape. The window of cosmic accessibility is open now, wider than it will ever be again, and it is closing. A species that achieves light-speed travel today has access to more of the universe than any species that achieves it a billion years from now. The laws of physics impose a deadline not just on individual journeys, but on the very possibility of intergalactic reach. There is a visceral way to understand what expansion does to light that is already in transit. Consider a photon emitted by a distant galaxy 10 billion years ago. At the moment of emission, that galaxy was much closer to us than it is today because the universe was smaller. The photon began its journey through a younger, denser, more compact cosmos. But as the photon travelled, the space behind it expanded. The galaxy that emitted it was carried to ever greater distances by the stretching of space. The photon, moving at the cosmic speed limit, covered ground through local space at 300,000 kilometers per second. But the cumulative expansion of all the space between the photon's current position and its origin meant that the origin kept receding. Simultaneously, the space ahead of the photon also expanded. The photon's destination, our region of the cosmos, moved farther away from the photon's starting point. But the photon was already closer to the destination than to the origin, so the expansion ahead was less severe than the expansion behind. The photon gained ground relative to the destination, while losing ground relative to the source. After 10 billion years of this asymmetric tug, the photon arrives at Earth. We detect it with our telescopes and measure its redshift, the stretching of its wavelength caused by the cumulative expansion it traversed. A photon emitted as ultraviolet light might arrive as infrared. A photon emitted as visible light might arrive as a microwave signal. The redshift quantifies how much the universe expanded during the photon's journey. For the most distant objects in the observable universe, the redshift is extreme. Galaxies with redshifts exceeding 10 emitted their light when the universe was less than 500 million years old. Those photons have been travelling for over 13 billion years. During that time, the expansion of space stretched their wavelengths by a factor of more than 11. The galaxies that emitted these photons now lie at moving distances exceeding 30 billion light-years, carried to these extreme separations by 13 billion years of cumulative expansion. These galaxies are visible but unreachable. The light we detect from them is ancient, emitted during an era when the universe was compact enough for photons to successfully make the journey. But the galaxies themselves now sit far beyond the cosmic event horizon. No signal we send today, no traveler we launch tomorrow, no probe we dispatch at any point in the future will ever reach them. The photons that carried their images to us represent the last contact. One way, one time, permanently concluded. This introduces a distinction that cuts to the heart of the cosmic distance problem. The observable universe and the reachable universe are not the same thing. The observable universe is defined by the past, by light that has already travelled to us from across cosmic history. The reachable universe is defined by the future, by the distances a light-speed signal or traveller can cover, given the ongoing and accelerating expansion of space. These two volumes overlap but differ enormously in size. The observable universe is roughly 20 times larger in radius than the reachable universe, and over 400 times larger in volume. We live inside a cosmic bubble of visibility that vastly exceeds our cosmic bubble of accessibility. We can see far more than we can ever touch. The universe has been generous with its light, but merciless with its distances. Now let us trace the future consequences of accelerating expansion, not in abstract terms, but in concrete cosmic events. Within the local group, gravity holds. The Milky Way and Andromeda will merge in approximately 4 to 5 billion years, combining into a single massive elliptical galaxy. The smaller member galaxies of the local group will be absorbed into this merged structure or scattered into close orbits. Gravity within this cluster is strong enough to resist cosmic expansion permanently. The local group is our lasting inheritance. Beyond the local group, every structure is being carried away. The Virgo cluster, currently the nearest major galaxy cluster at 54 million light-years, recedes at approximately 1,100 kilometers per second. This recession will accelerate as dark energy intensifies. Within roughly 100 billion years, the Virgo cluster will cross beyond the cosmic event horizon. Its light will be redshifted to wavelengths too long to detect. Its galaxies will fade from the observable sky and vanish permanently. The same fate awaits every galaxy cluster, every supercluster, every filament of the cosmic web that lies beyond our gravitational neighborhood. One by one, over billions and tens of billions of years, the structures of the cosmos will be carried beyond the event horizon by the accelerating tide of expansion. Each departure is permanent. No reversal is possible. Dark energy does not weaken, expansion does not slow. The tide flows in one direction, and it flows forever. Within approximately 2 trillion years, the last external galaxies will fade from detectability. Future observers within the merged local group remnant will look outward and see nothing. Empty space in every direction. No galaxies, no clusters, no filaments, no cosmic web. Just a single massive galaxy hanging in infinite apparent darkness. The cosmic microwave background, the afterglow of the Big Bang that currently permeates all of space at a temperature of 2.7 Kelvin, will also vanish. Expansion stretches the wavelength of this radiation continuously. As space doubles and doubles again over cosmic time, the microwave background shifts from microwave frequencies to radio frequencies, from radio frequencies to wavelengths measured in meters, then kilometers, then astronomical units. The energy per photon drops to levels that no conceivable detector could register. The oldest light in the universe, the radiation that carries the fingerprint of cosmic birth, will be diluted into undetectable silence. The fading will not happen all at once. It will unfold as a slow cosmic dimming, played out across timescales that dwarf the current age of the universe. Within roughly 50 billion years, the most distant galaxy clusters currently visible will cross beyond the event horizon. Their light, already ancient and deeply redshifted, will stretch past the detection thresholds of any instrument that physics permits. They will not explode or collapse or be destroyed. They will simply fade from the observable sky like ships sinking below a maritime horizon, mast by mast, sail by sail, until the last glimmer of reflected light vanishes beneath the curve of expanding space. Over the following hundreds of billions of years, closer structures will follow. The great superclusters, the massive galaxy clusters, the modest galaxy groups that populate the cosmic web between our local group and the distant reaches of space, each will be carried beyond the event horizon in turn. One by one, the lights go out. Not because the galaxies die, though many of their stars will have aged and cooled by then, but because the space between us and them has expanded beyond the capacity of light to bridge it. They continue to exist. They continue to burn. They simply exist and burn in a region of the cosmos that our corner of reality can no longer access or observe. The process resembles watching a vast city from a departing train. Building after building slides past the window and disappears behind you. At first, you can still see the skyline, the tallest structures still visible above the horizon. Then even those sink from view. Eventually, there is nothing behind you but empty track and open countryside. The city still exists, its lights still burn. But from your vantage point, it is as though it was never there, except this train never stops, and there is no return journey. Without external galaxies, future astronomers will have no evidence for cosmic expansion. Without the cosmic microwave background, they will have no evidence for the Big Bang. Without redshift data from distant objects, they will have no evidence for dark energy. The three pillars of modern cosmology, the expanding universe, the Big Bang origin, and the accelerating expansion, will be erased from the observational record, not hidden, not obscured, erased. The evidence will have physically departed the observable universe, carried beyond the event horizon by the very force those observations revealed. This is perhaps the most haunting consequence of accelerating expansion. Not just the loss of access, the loss of knowledge, the loss of the very possibility of knowledge. Consider what a brilliant physicist in that far future epoch could deduce. They would observe a single enormous galaxy, the merged remnant of the local group, containing perhaps 1 trillion aging stars. They would measure the motions of those stars, catalogue their chemical compositions, study the remnants of ancient stellar explosions. They would develop sophisticated theories of stellar evolution, nuclear physics, and gravitational dynamics. Their science might be extraordinarily advanced within its observational domain, but they would have no reason to suspect that the universe was ever anything other than what they observe. A single galaxy in infinite static space, no expansion, no Big Bang, no cosmic microwave background, no dark energy, no cosmic web, no 2 trillion galaxies stretching across 93 billion light-years. The entire cosmological framework that we have painstakingly assembled over the past century, the understanding that represents arguably the greatest intellectual achievement of our species, would be not merely unknown to these future scientists. It would be unknowable. The evidence required to construct it would have been physically removed from reality as they can access it. They might develop alternative cosmologies. Perhaps they would conclude that their galaxy has always existed, eternal and unchanging. Perhaps they would hypothesize a creation event but lack any empirical means to confirm it. Perhaps their most brilliant minds would propose that other galaxies once existed, scattered throughout a larger cosmos, but they would have no way to test this hypothesis. It would remain speculation, unfalsifiable, indistinguishable from mythology. The truth about the universe would be classified as philosophy rather than science, because the boundary between the two depends on evidence, and the evidence would be gone. We are living in the only epoch during which the full story of the cosmos is empirically accessible. The evidence is here now. The cosmic microwave background still glows at 2.7 Kelvin. Distant galaxies still dot the sky in every direction. Redshift measurements still reveal the expansion of space. The acceleration driven by dark energy is still detectable through observations of distant supernovae. Every component of the cosmological picture is currently available for investigation. This window is temporary. It has been open for roughly the last 13 billion years and will remain open for perhaps another 100 billion. After that, the evidence fades beyond recovery. The story of the universe becomes untellable by any observer confined to a single gravitational structure. We are not merely fortunate to exist during this window. We are cosmologically privileged in a way that no future civilization, no matter how advanced, can replicate. They will inherit better technology. They will possess greater computational power. They may develop physics far beyond our current understanding, but they will lack the one thing we have that cannot be manufactured: a sky full of evidence. A civilization arising in that far future epoch would observe a single galaxy floating in static, empty space. Their most sophisticated telescopes would detect nothing beyond their own stellar population. Their cosmological models, built on the only available evidence, would describe a universe consisting of one galaxy in an infinite void. They would have no reason to suspect that trillions of galaxies once filled the sky, no reason to hypothesize an explosive origin, no reason to imagine that space itself was expanding. Their physics might be flawless within its observational domain, but cosmologically blind, missing the largest features of reality because those features have been swept beyond detection. This future scenario is not speculative fiction. It is a direct, calculable consequence of the measured cosmological parameters. The dark energy density, the current expansion rate, the deceleration parameter, the matter density. These values, confirmed through multiple independent observations, produce a future in which cosmic isolation is total and irreversible for any gravitationally bound structure. We happen to exist during the epoch when this isolation is still incomplete. The sky is still crowded with galaxies. The cosmic microwave background is still detectable. The expansion of space is still measurable. The story of the cosmos is still legible, written in the light that reaches us from every direction and every epoch. But this window is finite. The evidence is being erased in real time. Every second, photons from distant galaxies are stretched a little further toward undetectability. Every second, the cosmic event horizon contracts a little further, removing galaxies from our future reach. The observable universe dims slowly, imperceptibly on human timescales, but relentlessly on cosmic ones. There is one additional dimension of this problem that deserves attention before we move to its implications. Everything discussed so far concerns a light-speed traveler departing from our current position in space and time, but the cosmic event horizon applies universally. It constrains not just humanity but every civilization in the observable universe, regardless of location, regardless of technological advancement, regardless of when they arise. A civilization in the Virgo cluster faces its own cosmic event horizon, centered on its own position, with its own radius determined by the same cosmological parameters. Their reachable universe is approximately the same size as ours, roughly 16 to 17 billion light-years in co-moving radius. They can reach a comparable fraction of the observable universe, roughly 4 to 6%. They face the same accelerating contraction of their accessible volume. They will be isolated within their own local gravitational structure on the same cosmic timescale. This universality is crucial. The limitation is not local. It is not a peculiarity of our position in the cosmos. It is a global property of the universe itself, written into the geometry of space-time and the energy content of the vacuum. Every observer, everywhere, faces the same constraint. The speed of light is the maximum velocity. The cosmic event horizon is the maximum reach, and accelerating expansion ensures that this maximum reach decreases with time. No technology circumvents this. Faster-than-light travel is not merely difficult, it is prohibited by the structure of space-time, as described by general relativity. Wormholes, warp drives, and other speculative concepts remain firmly theoretical, requiring exotic matter with negative energy density that has never been observed and may not exist. Even if such technologies were somehow realized, they would face their own set of fundamental constraints imposed by causality, energy conservation, and the topology of spacetime. The cosmic event horizon is not an engineering problem awaiting a clever solution. It is a geometric feature of the universe, as fundamental as the curvature of spacetime around a massive object. This is the full picture of the expanding trap. The universe is not merely large, it is large and growing. Not merely growing, but accelerating. Not merely accelerating, but doing so in a way that permanently removes the vast majority of cosmic structures from the reach of any physical process, any signal, any traveler moving at any speed up to and including the cosmic maximum. The speed of light is the fastest possible traversal of space. The expansion of space defeats even this maximum velocity across the majority of cosmic distances. At the stellar scale, light speed costs millennia. At the galactic scale, millions of years. At the scale of the observable universe, billions. And beyond the cosmic event horizon, no cost suffices. The price is infinite, and the destination is permanently out of stock. The geometry is implacable. The contents of the cosmos sit at distances exceeding the reach of its own speed limit, and those distances grow faster than that speed limit can accommodate. The expansion of space is not a barrier that was erected to block us. It is a property of the fabric through which we move, as intrinsic to the cosmos as gravity or electromagnetism. What remains is to reckon with what this means. Not just for travel, not just for communication, not just for exploration, but for the nature of civilization itself, in a universe whose accessible fraction is finite and shrinking. If even the speed of light cannot carry us to most of what exists, what does that tell us about our place in the cosmos, and the meaning of looking up at a sky full of stars whose light arrives as a farewell rather than an invitation? Everything we have established across this journey collapses into a single, verifiable conclusion. We crossed our solar system in hours, reached nearby stars in years, confronted galactic distances that demand millennia, and watched intergalactic travel collapse under transit times measured in millions of years. We discovered that the expansion of space defeats even the cosmic speed limit across the majority of observable distances, and that accelerating expansion driven by dark energy is permanently removing 94% of visible galaxies from the reach of any physical process. Through confirmed physics and measured distances, every calculation pointed toward the same conclusion. The universe is not merely larger than light speed can conquer. It is structured in a way that guarantees light speed will never be enough. Now we must sit with what this means. Not for hypothetical spacecraft or theoretical physics, but for the lived reality of civilizations that arise, endure, and eventually perish within the boundaries that nature imposes. Start with stars, because stars are clocks. Every civilization that has ever existed or will ever exist depends on a star for energy. Stars are not permanent. They are fuel reserves burning through finite supplies of hydrogen at rates determined by their mass. Our Sun converts roughly 620 million metric tons of hydrogen into helium every second. It has been doing this for approximately 4.6 billion years and has enough fuel remaining for another 5 billion. When that fuel runs low, the Sun will swell into a red giant, engulfing Mercury and Venus, scorching the Earth into uninhabitability, and eventually shedding its outer layers to leave behind a white dwarf no larger than our planet, but containing half the Sun's original mass. This is not catastrophe. It is stellar biology. The life cycle of an average star, as predictable and inevitable as the seasons. Smaller stars burn longer. Red dwarfs, the most common stellar type in the galaxy, comprising roughly 70% of all stars, fuse hydrogen so slowly that they can sustain themselves for trillions of years. A red dwarf born today will still be shining long after the last sun-like star in the universe has died. These dim, patient furnaces represent the longest-lived energy sources available to any civilization. Massive stars burn fastest. Blue supergiants exhaust their fuel in mere millions of years, ending in supernova explosions that briefly outshine entire galaxies before collapsing into neutron stars or black holes. A civilization orbiting a massive star would have a cosmologically brief window of habitability before its sun detonated. The lifespan of a host star sets the first clock for any civilization. A species must either endure within the lifetime of its star or migrate to a new one. Light-speed travel, as we established in Part 1, makes stellar migration possible within limited ranges. A civilization around a sun-like star could, in principle, identify younger candidate stars within a few hundred light-years and dispatch colony missions that arrive within centuries or millennia of external time. The travelers would sacrifice their connection to home but preserve the species around a fresh energy source. This is the scale at which light speed genuinely functions. Within a bubble of a few hundred light-years, interstellar colonization remains conceivable for a sufficiently long-lived civilization willing to accept the temporal cost. The journeys are one way in every meaningful sense. The travelers depart one era and arrive in another. But the species propagates. Life continues around a new sun. The trouble begins when we ask how far this process can extend. A civilization that colonizes a star 200 light-years away has purchased another 5 to 10 billion years of stellar energy depending on the target star's mass. When that star begins to age, the colony must repeat the process, identifying yet another young star within reachable distance and dispatching another generation of colonists. Each hop covers a few hundred light-years and buys a few billion years. Over many such hops spanning tens of thousands of years of cumulative travel time, the civilization migrates slowly through the galaxy. This island-hopping strategy could theoretically allow a species to persist across the full lifespan of the Milky Way's stellar population. The galaxy will continue forming new stars for tens of billions of years, though the rate of star formation is already declining from its peak roughly 10 billion years ago. As long as fresh stars ignite somewhere within reachable distance of existing colonies, the chain of migration can continue. But the chain has limits imposed by stellar evolution at the galactic scale. Star formation requires cold molecular gas, primarily hydrogen, that collapses under gravity into dense cores where nuclear fusion ignites. The Milky Way currently converts approximately 3 solar masses of gas into new stars each year. This rate has been declining for billions of years as the galaxy's gas reservoir is gradually consumed. Eventually, the raw material for new stars will be exhausted. Existing stars will age and die without replacement. The galaxy will transition from a vibrant stellar nursery into a graveyard of cooling remnants. This stellar endgame unfolds over trillions of years for the lowest mass red dwarfs, but the transition from active star formation to stellar senescence begins much sooner. Within roughly 100 billion years, the rate of new star formation in the Milky Way will drop to negligible levels. Most remaining stars will be ancient red dwarfs burning through the last of their hydrogen. The supply of fresh, young stars available for migration will dwindle. A civilization pursuing the island-hopping strategy will find fewer and fewer viable destinations, separated by ever greater distances as the stellar population thins. Eventually, the last star in the galaxy will exhaust its fuel and fade. Current astrophysical models place this final stellar death roughly 100 trillion years in the future, when the last red dwarfs burn through their hydrogen and cool into inert brown dwarfs. After this point, no conventional energy source remains. The galaxy goes dark, not suddenly, but gradually, like a city losing power district by district over billions of years until the last streetlight flickers out. A civilization that has migrated across the galaxy for trillions of years, hopping from star to dying star, finally confronts a cosmos without fuel. No new stars form, no nuclear furnaces burn. The only remaining sources of energy are gravitational contraction, the slow cooling of white dwarfs and neutron stars, and the inconceivably slow process of black hole evaporation through Hawking radiation. This is the deep future of any galactic civilization, regardless of its technology. Light speed grants access to the stars within a galaxy, but cannot prevent the stars from eventually dying. The gift of cosmic maximum velocity extends the reach of a species, but cannot extend the lifespan of the energy sources it depends upon. The stellar clock runs down for everyone. Beyond the galaxy, the situation is even more constrained. We have already seen that intergalactic travel at light speed demands millions to billions of years, and that accelerating expansion removes the vast majority of external galaxies from any possible reach. A civilization confined to its local gravitational structure, the merged remnant of the local group in our case, must make do with the stellar resources within that structure. No resupply missions from distant galaxy clusters, no imports of fresh hydrogen from the cosmic web. The gravitational neighborhood is all there is, and its contents are finite. The merged Milky Way Andromeda galaxy, sometimes called Milkdromeda, will contain roughly 1 trillion stars after the collision completes in 5 to 6 billion years. Over the following tens of billions of years, as smaller local group members fall inward and merge, the total stellar inventory may grow modestly. But the gas reservoir is finite. Star formation will peak during the collision, as gravitational interactions compress gas clouds and trigger intense bursts of stellar birth, and then decline steadily as available gas is consumed. The merged galaxy will shine brilliantly for a few billion years and then slowly dim. 1 trillion stars is an extraordinary inheritance. Even if only a fraction host habitable planets, the number of potential homes for life within the merged local group remnant is staggering. Billions of worlds, perhaps tens of billions, each offering a platform for civilization to arise, flourish, and endure. Light-speed travel connects these worlds across timescales measured in tens of thousands of years for galactic crossings, permitting slow but real exchange between far-flung colonies. But the local group is a closed system. Nothing enters from outside. The cosmic event horizon ensures that no matter, no energy, no information from the broader universe will ever supplement what gravity has already gathered. Every atom within the local group at the moment of cosmic isolation represents the total material budget for all future civilization within this structure. When those atoms have been cycled through stars and planets and living organisms enough times, when the last hydrogen has been fused and the last stellar furnace has cooled, the lights go out permanently. This is not a failure of ambition. It is not a failure of intelligence or technology or will. It is the thermodynamic endgame of a finite energy supply in an expanding universe. Every bound gravitational structure in the cosmos faces this identical fate. The details vary. Some galaxy clusters are larger, containing more gas, more stars, more raw material. Their stellar eras last longer. Their civilizations have more room and more time. But every structure is finite. Every fuel supply runs out. Every light eventually goes dark. Against this backdrop of cosmic mortality, the question of what we can reach acquires a different weight. Light speed gives us access to our galaxy and the local group. It permits migration between stars across timescales that, while immense, fall within the theoretical endurance limits of a sufficiently robust civilization. It allows a species to persist for trillions of years by following the light from one dying star to the next still burning one. This is not a small gift. Trillions of years of potential existence, spread across billions of worlds, exploring a merged galaxy containing 1 trillion stellar systems. By any terrestrial standard, this is a staggering inheritance. But it is bounded. The walls are real. The expansion of space ensures that the overwhelming majority of the cosmos remains forever beyond contact. The finite lifetime of stars ensures that even the accessible regions eventually go dark. A civilization can burn brightly for an almost inconceivable duration, but not forever, and it can explore a vast but limited volume, never the whole. There is something in this picture that resists despair, something that, approached with the right frame of reference, inspires awe rather than grief. to see it requires stepping back from the mathematics of expansion and time dilation and considering what the universe actually produced within these constraints. Roughly 13.8 billion years ago, the universe consisted of a nearly uniform sea of hot plasma. No structure existed, no stars, no planets, no molecules, just a featureless expanse of energy and elementary particles expanding outward from the initial singularity. Tiny quantum fluctuations, variations of 1 part in 100,000 in the density of this primordial soup, represented the only departure from perfect smoothness. From those fluctuations, gravity built everything. Over hundreds of millions of years, slightly denser regions pulled in surrounding matter, growing incrementally, collapsing into the first stars. Those stars burned through their hydrogen and exploded, seeding the surrounding gas with heavy elements: carbon, oxygen, nitrogen, iron, the raw materials of chemistry. New generations of stars formed from this enriched gas, now capable of producing rocky planets with complex molecular surfaces. On at least one of those planets, chemistry became biology. Simple self-replicating molecules gave rise to cells. Cells organized into organisms. Organisms diversified into ecosystems, spanning an entire world. And from one lineage of primates on one unremarkable continent, a species emerged that could contemplate the process that created it. This arc, from quantum fluctuations to conscious observers, unfolded entirely within the constraints we have described. Light speed limited every interaction, expansion stretched every distance. Stellar lifetimes set every clock, and yet, within these boundaries, the universe produced complexity, beauty, and awareness on a scale that no initial inspection of the laws of physics would have predicted. Consider what it means to understand the cosmic event horizon from inside it. We are a species that evolved to track prey across savannas, to judge distances to nearby trees, to remember the locations of water sources within walking range. Our perceptual systems are calibrated for a world measured in meters and kilometers. Our temporal intuitions are built for seasons and lifetimes, spans of decades at most. And yet, from this narrow cognitive platform, we deduced the age of the universe to within 1%. We measured the cosmic microwave background to millionths of a degree. We calculated the expansion rate of space. We discovered dark energy. We mapped the large-scale structure of the cosmic web across billions of light years. We derived the existence of the cosmic event horizon through mathematics and confirmed its implications through observation. No other process in the known universe has accomplished anything comparable. Stars burn with tremendous energy, but they do not know they burn. Galaxies organize themselves into breathtaking structures, but they do not comprehend their own architecture. Black holes warp space-time to extremes, but they possess no awareness of the distortions they create. Consciousness, as far as we can determine from every observation available, is the rarest and most extraordinary phenomenon in the cosmos. And it arose here, within the constraints, within the boundaries, on one small world orbiting one average star. And the universe did not need to produce observers. Nothing in the laws of physics mandates consciousness. The equations of general relativity, quantum mechanics, and thermodynamics function identically whether or not anyone is present to witness them. Stars form, burn, and die, regardless of observation. Galaxies collide and merge in darkness. The expansion of space proceeds whether or not any species ever looks up and measures it. But the universe did produce observers. It produced beings capable of calculating the cosmic event horizon, understanding why it exists, and grasping what it means. This is not a trivial accomplishment. This is, as far as we can tell, the most improbable and significant event in the history of the cosmos. A collection of atoms organized by billions of years of stellar and biological evolution looked outward and understood the structure of everything. That understanding carries a peculiar form of power. Not the power to overcome the speed of light, not the power to halt the expansion of space, not the power to reach the 94% of galaxies that lie beyond our event horizon, but the power to comprehend what exists beyond reach, to know its scale, to calculate its properties, to appreciate its architecture even though we can never physically explore it. Telescopes are not substitutes for starships. Observation is not the same as visitation, but observation is not nothing. The Hubble Space Telescope, the James Webb Space Telescope, and their successors grant us detailed portraits of galaxies billions of light-years away. We study their star formation histories, their chemical compositions, their morphologies and dynamics. We watch collisions between galaxy clusters that occurred when our sun had not yet formed. We detect the faint afterglow of the universe's birth encoded in microwave radiation that has travelled for 13.8 billion years to reach our instruments. Every photon that arrives from beyond the cosmic event horizon carries information about a region we can never visit. Those photons are one-way messages, dispatched billions of years ago from sources that have since receded beyond all contact. They are the last emissaries from an unreachable cosmos, and they carry enough information for us to reconstruct the history, structure, and fate of the universe on the largest scales. We are map makers, charting a territory we can never walk. And the map is extraordinary. The cosmic web, with its filaments and voids and clusters, reveals a universe organized on scales that dwarf every human reference frame. The cosmic microwave background reveals the initial conditions from which all structure grew. The accelerating expansion reveals the long-term fate of everything that exists. Each discovery expands the map, adding detail and depth to a portrait of reality that no single civilization could ever physically verify through exploration alone. There is also this: the constraints that limit our reach are the same constraints that made our existence possible. The speed of light governs not just travel but the rate of information transfer, the strength of electromagnetic interactions, and the stability of atomic structure. If light moved faster, the universe would be a fundamentally different place, with different chemistry, different stellar physics, and possibly no pathway to complex life at all. The expansion of space created the conditions for galaxy formation by stretching initial density fluctuations to scales where gravity could amplify them into cosmic structures. Dark energy, the very force that drives galaxies beyond our reach, may play a role in regulating the large-scale smoothness of the universe that permits stable galactic environments. The boundaries are not incidental to our existence. They are woven into the same physics that produced us. The universe is not a prison. It is a landscape of extraordinary scale, governed by rules that simultaneously enable complexity and limit reach. Those rules produce stars, planets, chemistry, biology, and consciousness. They also produce distances that no velocity can conquer, timescales that no lifespan can span, and an expansion that no technology can reverse. Both the gift and the constraint emerge from the same equations. Both are consequences of the same physics. Celebrating one while lamenting the other misses the point. They are inseparable aspects of a single reality. What, then, should a conscious species do with this knowledge? We explore what we can reach. Within the Milky Way, hundreds of billions of star systems await investigation. Each is a unique experiment in planetary formation, harboring worlds shaped by different compositions, different orbital dynamics, different stellar environments. Some may harbor life, some may harbor intelligence. The diversity of possible worlds within a single galaxy exceeds anything human imagination has yet conceived. We observe what we cannot reach. The light from distant galaxies carries the history of the cosmos. Every photon is a data point. Every spectrum is a biography. Every image is a chapter in the longest story ever told. We cannot visit these sources, but we can read their messages and build an understanding of the universe that transcends our physical limitations. We endure as long as the physics allows. A civilization that manages its stellar resources carefully, migrating between stars as each one ages, could persist for trillions of years within the merged local group remnant. Trillions of years of accumulated knowledge, trillions of years of cultural evolution, trillions of years of scientific discovery conducted across billions of worlds. The scale of potential experience available within our cosmic inheritance dwarfs any individual human life by factors that make the comparison meaningless. And we remember what the sky once looked like. If future civilizations arise in the dark epoch after external galaxies have vanished beyond the event horizon, they may never know that the cosmos once teemed with visible structure. The knowledge we have gathered now, in this brief cosmological window when the evidence is still legible, may represent the only record that will ever exist of the universe's true scale and history. Preserving that knowledge across cosmic time is not merely an academic exercise. It is the conservation of the most profound truth any species has ever uncovered. The speed of light is not slow. It is the fastest phenomenon in the physical universe. A photon crosses a room in a billionth of a second. It reaches the moon in barely over a second. It spans the solar system in hours. It bridges the gaps between nearby stars in years. It is magnificent, and the universe is more magnificent still. Its structures span billions of light years. Its history stretches across 13.8 billion years. Its expansion outpaces its own speed limit across the majority of observable distances. Its inventory of galaxies, stars, and planets exceeds the capacity of any consciousness to fully enumerate. We cannot reach most of it. We were never going to. The distances were always too vast, the expansion always too relentless, the stellar lifetimes always too finite. The universe was never ours to conquer. It was ours to witness, to measure, to understand, and to stand in awe of, knowing that the same laws which bind us to one small corner of an infinite expanse also gave us the minds to comprehend what lies beyond. The stars are not beyond our understanding, only beyond our reach. And in the end, understanding may be the longer voyage, the deeper exploration, and the more enduring legacy. We are a species that looked up from one pale world and saw the shape of everything. That is not a small thing. In a cosmos this large, it may be the most extraordinary thing that has ever happened.